It stands by the water's edge, a seemingly simple creature embodying a biological impossibility. To fly demands lightness and grace. To swim requires density and propulsion. To walk demands structural stability. Yet, the duck achieves all three, seamlessly transitioning between elements in a way that defies engineering logic. What hidden, unified chassis allows this organism to violate the fundamental laws of locomotion, and what secrets of advanced adaptation are stored within its unassuming form? In the realm of advanced robotics and bioengineering, the creation of a single platform capable of high-efficiency performance across air, water, and land remains the holy grail. We build drones for the sky, submarines for the deep, and rovers for the surface, each optimized for a single medium. The duck, however, operates as a single, multimodal system, achieving near-optimal efficiency in three profoundly different physical domains. This is not just a bird. It is a masterclass in compromise and anatomical genius. Tonight, we will deconstruct this biological machine, examining the unseen trade-offs, the subtle adjustments, and the evolutionary algorithms that solve the unsolvable engineering problem of the triple threat. To conquer the air, the duck required the fundamental avian blueprint: a lightweight frame, hollow bones, and powerful flight muscles anchored to a deep keel. However, unlike a true aerial specialist, the duck is built with a necessary weight penalty: the density required for its aquatic life. Its body must be compact and robust, designed to absorb the impact of landing on water and to resist cold temperatures. This means its flight is a compromise, efficient enough for migration and escape, but lacking the high-speed agility of a falcon or the soaring endurance of an albatross. The duck sacrifices ultimate aerial performance for the essential ability to remain airborne when necessary. The plumage of the duck is the first true piece of advanced adaptive technology. Each feather is a complex nanostructure, coated in an oil secreted by the uropygial gland, making it virtually waterproof. This isn't just insulation, it's a dual-function system. In the air, the feathers lock together to form the perfect, smooth airfoil required for lift and drag reduction. In the water, this oily, tightly packed layer traps a cushion of air against the skin, providing crucial buoyancy and thermal isolation. The plumage is the duck's environmental control system, capable of optimizing performance and protection in two radically different physical states simultaneously. The duck's swimming mastery stems from its body shape, a perfect hydrodynamic hull. Its low riding profile and the absence of external ears and a prominent tail create minimal drag underwater. Propulsion is achieved not through continuous flapping like a fish, but through the precise, symmetrical power of its legs. Unlike the continuous, full-body motion of an aquatic mammal, the duck's engine is entirely localized in its rear. The legs, thick and muscular, act as a synchronized pair of high-powered, foldable paddles, driving the bird forward with surprising speed and agility, allowing it to navigate currents and pursue prey with efficiency. The famous webbed foot is the masterpiece of the duck's triple threat. On the forward stroke underwater, the toes spread wide, and the web stretches taut, creating a large surface area for maximum push, acting as a massive paddle blade. On the recovery stroke, the toes rapidly fold inward, compressing the web against the ankle. This folding action minimizes the water resistance on the return stroke, optimizing the cycle for forward propulsion. The foot is, in essence, a self-adjusting, variable geometry propeller, a solution that still challenges naval architects attempting to design efficient, silent underwater propulsion systems. The duck's waddle is not a sign of poor design. It is the inevitable trade-off for its aquatic superiority. The webbed feet, optimized for paddling, are necessarily wide and set far apart, positioned near the rear of the body. This posterior placement is perfect for steering and power generation in water, but on land, it shifts the center of gravity far forward. To maintain balance while walking, the duck must shift its weight side to side with every step, resulting in the characteristic, often comical waddle. The clumsy movement on land is the price of efficiency in the ocean, a perfect example of a system sacrificing ground mobility for superior multi-element performance. The ability to perform in three mediums requires a complex algorithm for bone density. The duck's bones are light enough to fly, yet strong enough to withstand the forces of paddling and the repetitive impact of terrestrial walking. The solution lies in the microarchitecture of the bone tissue. While generally lighter than mammal bones, they exhibit localized density in the legs and feet to handle impact and muscle torque, while retaining a more pneumatic, lighter structure in the wings and the main torso. The duck's skeletal system is an intelligent structural composite, minimizing mass where required for lift and maximizing strength where required for propulsion. Beyond the physical architecture, the true marvel is the central processing unit, the duck's brain. The rapid transition between modes requires instantaneous neurological mode switching. The brain must swiftly calculate new aerodynamic or hydrodynamic requirements, adjusting muscle tension, wing angle, and web deployment in milliseconds. This ability to instantly recalibrate its entire locomotive algorithm, prioritizing flight, diving, or walking without delay, is a testament to an efficient, low-latency nervous system, a biological computer that seamlessly manages multimodal tasks. The duck remains a profound challenge for biomimicry and robotics. Engineers are attempting to create unmanned aerial aquatic vehicles that can fly efficiently and then transition to swimming. The problem is always the wing. A large wing is terrible in water. A small fin is useless in the air. The duck solves this by using the wing for two completely different forms of flight and using the foot as a versatile, compact propulsion system. The duck's solution is a reminder that the most elegant engineering may involve combining rather than separating functions. By studying the duck's anatomy, we gain critical insights into the future of human mobility platforms. Imagine delivery drones that can land in water, transition to high-speed underwater navigation, and then waddle out onto a dock. The duck holds the foundational code for systems that must operate in variable density environments, offering a roadmap for true all-terrain, all-element vehicles. Its seemingly simple biology hides the key to complex, cross-domain locomotion. We began by questioning the duck's triple superpower and discovered a unified system built on necessary compromise and brilliant, localized adaptation. The waddle is the price of the paddle. The feathered armor is the key to both lift and insulation. The duck is not just a bird that flies, swims, and walks. It is an optimized machine that teaches us that true efficiency in a complex world requires shedding the pursuit of absolute perfection in one domain for the mastery of simultaneous adequacy in many. Its unassuming form holds a blueprint for the future of robotics and engineering. What other seemingly simple creatures hold the complex, optimized code to the next great technological leap?